So we left off last week. We were talking about EMR. Can anybody fill us in on any of the details about EMR that we learned? So where is EMR typically sourced from when we're doing remote sensing? Yeah. What's it reflect off of? Anything that sunlight hits, exactly. So in our case, being here on the face of the earth, that is what? The face of the earth, right? Yeah, that's typically what we're gathering remote sensing data for. Of course, you can't do it for other planets too. So yes, literally anything that the sun hits. What's the wavelength and frequency of EMR have to do with anything? Right here in front.
So like different wavelengths will show different information. So if you do wavelengths respond and like in retrospect to like color, you can see color, but you can also use different wavelengths to look at like long wave and short wave radiation, for example.
So how's that tie into frequency? Somebody else.
The higher the frequency, the shorter the wavelength.
The higher the frequency, shorter the wavelength. Right? So give me an example of a long wavelength EMR. Radio. Yes, the cell frequencies. Give me an example of a high frequency type of EMR. MRI, gamma, extremely high X-ray. Yes, yes, yes.
The stuff that gives you cancer.
Exactly. Yep, the stuff that passes right through your body. Light's nice; it'll hit your body without penetrating, but it's the stuff that can penetrate your body that typically comes with weird side effects. All right. I think that's good. So we're going to transition here into some different terminology surrounding radiation. We have like 15 slides to get through here from last week. I'm going to try and keep it quick. And then we'll transition into week 3 stuff, which is all about aerial photography and some basics in photogrammetry. And then our lab for the week, lab 2, is going to be pre-processing some images in Envy. And I've got some commercial satellite data for that. So where we used open source Landsat data, or publicly available, I shouldn't say open source, Landsat data last week. This week we'll be using commercial data. So in this little section here, we're going to talk about like what exactly remote sensing measures, and then what you are looking at in a remote sensing image. So we're typically measuring radiant energy. This is denoted as Q. Its units are in joules. And this is the amount of energy that is traveling in the form of EMR. So we measure this in joules. The radiant flux is that energy being emitted from an area. So each pixel represents an area on the surface of the Earth. So the radiant flux is the radiant energy, which is transferred from that pixel. And this is in, I don't know, it looks like the units got messed up here. So that is in joules per area per time. It's okay. You know, you can set up the text message to do that, right? Oh, it only took me a year to figure that out. All right, so when radiant energy or any related quantities measured in terms of its chromatic components, when it's only one type or one color, one type of EMR or one color, it becomes a function of wavelength. So that means that the radiant energy is directly correlated to wavelength there. So when we have designations for those types of relationships, we add a spectral in there. So instead of just being radiance, this is where we get the term spectral irradiance. So when we look at spectral irradiance, we're looking at radiance across the entire spectrum of EMR, and not just one pixel. Or sorry, not just one segment of the spectrum. So when we see this, we add the wavelength symbol. So that means that we're looking at the radiance or the radiant energy from this slide for one specific location in the EMR spectrum. So that's when we denote the wavelength that we are investigating. So I mentioned that when we're talking about a flux, we're typically associating it with an area on the surface of the Earth. So here, this concept is used to explain irradiance and excidence. So irradiance is the measure of EMR to an area. So this is this being the surface of our Earth. Here's the area that we're investigating. So the irradiance is the measure of incoming EMR energy to that surface per unit time. So this is in watts per square meter. And then if you have a constant EMR source, this can also be expressed over time. So you've got your radiance over an area to give you the flux density. For excidence, excidence is after we've had EMR interact with our surface, being reflected. Excidence is the measure of the radiant flux leaving a surface per unit area. And this is also in watts per square meter. And similarly, so here is our excidence equation. So the radiant intensity is a measure of intensity for a radiating surface. A lot of times this is related to the angle at which EMR interacts with the surface or reflects off the surface. So after the reflection is emitted, it forms a solid angle, which is noted by omega here, and heads toward our detector. So here the intensity is related to the irradiance and our solid angle. So the larger the solid angle, the less intense or the smaller radiant intensity we are going to have. And this is measured in watts per steradian. Does anybody know what a steradian is? So in the, I guess in two-dimensional geometry, a radian is an expression of an angle, correct? So a steradian is in three-dimensional geometry, where we are expressing the angle in 3 dimensions. So 1 steradian is equal to the circumference of a circle, 2 pi r. And that's an intersecting circle with a sphere, the surface of a sphere. And that's all because that your EMR, after it interacts with the surface, after it reflects off the surface, it's being projected out in 3 dimensions, not just 2.
What are the what's the symbol that the question marks are representing?
I believe that's just a numeric value. So there would be, in the real world, we would have a number times your constant. So we can look at how exactly we calculate this. So given our source area, so this is what we are studying on the ground here. The projection of this area to our camera is expressed here. And this is known as, A cosine theta. So the cosine theta comes from the angle of our detector in relation to normal of the surface that we're studying. So this angle right here. And A is our source area. So we're correcting our original area for being at an angle. And we have our flux divided by the solid angle. So the solid angle is what is in between here. And rather than being thought of as a 2-dimensional angle, it's a 3-dimensional angle. So it's more like a cone. And this is expressed as an area as well. So here is the definition of that. So radiance, the radiant flux per unit solid angle. So solid angle being the space that it is, the cone of projection as EMR leaves the surface, leaving an extended source in a given direction per unit projected source area. In that direction, and it's measured in watts per meter, watts per meter squared per steradian. So watts being a flux that has to be associated with an area, and this is all based on the unit of a steradian. And remember, we get our wavelengths when we're only investigating certain wavelengths. So when you see that notation, know that we're not looking at the entire EMR spectrum anymore. So when you see sub gamma, that is when we're looking at a specific wavelength or specific frequency of EMR. And of course, we're always studying a source area. So source area is noted by the A, and our direction is the angle between normal to our surface. So this being our surface that we're looking at here, normal being 90 degrees from that, and theta being the difference between normal and our detector.
I have a question.
Yeah.
Is this affected at all by the angle of the emitter? Like, so if the sun
Yeah,
is,
yeah.
So
absolutely.
we're looking at what's coming out. But this is also affected by the angle of where the emitter is
Yep.
too, right?
Yeah, and I mean, you also have to take into account that the surface of the earth is not flat and it's not, I mean, it's also curved too. Yeah. So if you're looking at big enough scene, images that are further off in the distance will be colored differently because of this.
And if
And
the sun's at a lower or higher angle in the sky.
yeah, absolutely. Yeah, it reflects off different features in different ways. I mean, some features that would be, I mean, like look at the side of a building when the sun is shining on it versus to when it's in the shade. So I mean, you get weird effects within that. You get weird effects with the curvature, and also what we'll see with some of the photogrammetry slides too. You can there's even weird optical effects that are present just from the center of an image versus like the outer edges of the image too.
But in this formula, the angle of the emitter isn't represented anywhere on this formula.
Correct. Yep. Yeah. So yeah, this is specifically about leaving and heading to hopefully our eyes or our receptor. Yeah. Anybody else have any questions about this? All right. So not to terrify you, but these are some of the different notations that we'll be using throughout the semester. So if you need like a list of what is what, I like to tuck this away in these slides for you to come back and reference when you see a variable and you're like, hey, what the heck is that? I can't remember. So I put this here to hopefully help you. So we're not going to go down into the details of this. This is just to show you how complex getting the total radiance typically is. The diagram here, get rid of these zoom controls. So the diagram, you can see the different steps, you can see the different like inputs to the equation here. And we can see the different parts that are all I guess, part of the bigger radiance calculation. We'll look back at this a couple times throughout the semester as we get into numerical applications. So another interesting effect that is not because of geometry or angular effects of EMR interacting with different surfaces. Another thing that we have to deal with is atmospheric, typically hazes is what we deal with mostly. Complete clouds you can't really correct for. But when we have hazy images or partial cloud cover like this, we can typically remove those hazes and get to a usable image. So this is just one method of atmospheric correction. This is called a method called AtCore. And we'll look at some different atmospheric correction methods next week in lab. So in a little bit of recap, we talked about the wave and particle models. We talked about scattering, reflections, absorption, all the different interactions that can happen during EMR transmission. We talked a little bit about digital numbers. That was mostly in the lab last week. That we touched on that. We'll come back to digital numbers today with lab and also next week when we start talking about different parts of digital images. Sensors record reflected energy in a solid angle. What they are detecting is called reflectance. So you should be able to answer for me Why does one cat appear to be white and why does another appear black? Not the biological answer.
Pigmentation.
White one scattered all the light. And black one absorbed.
Yep. Anybody, everybody hear that? Yep. So white scatters all light, reaches our eyes, so we see all light. The black does not scatter. So it's absorbing all light. Yep, there's the answer. Here's another one for you. So, can we use anything else aside from EMR in remote sensing? Who said yes? What can we use?
We're using radio waves.
That's EMR, right?
Oh,
Use sound
We
waves.
stumped one. Sound waves. Sound waves, definitely one. That is not a form of EMR. How about seismic waves? Yeah, it's a pretty cool form of remote sensing. Any other examples? What? Sixth sense?
Mom's eyes in the back of her head when I was a kid.
Yeah, there you go. Yeah. Has anybody seen the Titanic movie? Super cheesy, but there's a really cool bit of remote sensing. They actually use the waves on the surface of water. Yeah. Water waves. They're firing a projectile out and mapping, they're triangulating it's actually trilateration, not triangulation. But they're pinpointing the different locations that they're shooting their like projectiles at based on the buoys bouncing up and down. Pretty cool. It's a terrible movie, but pretty sweet.
Well, I have to ask, did they actually use that to find it then for real world instead of like referencing? Like, did they use that for finding it in the mid-90s then?
Oh, I have no clue. That's a great question. I don't know the origin of like,
How they, okay.
yeah. So sound is the one that they give. We came up with other examples. I guess seismic waves are, I guess technically just sound waves. And what's our last one here? Yeah, so how about this one? So when you can see just like a crescent of the moon, you can usually see a little bit more. Where's that extra light coming from? Because it's not like an abrupt transition to black. It's a soft transition. Why is it a soft transition? Because I mean, the sun is, it's only reflecting, I mean, we can only see part of the sun's reflection on it. Curved surface,
First try.
Reflecting from Earth?
possibly, it could be reflecting from Earth. What else does the moon have?
Craters.
Craters. Could be something, there could be something in the craters, maybe some aliens. How about an atmosphere? Has a little bit of an atmosphere, right? Let's see what the answer here says. So there you go, it's the Earth. Who said the Earth? Woo, not the craters. Does anybody have any questions about the lecture 2 or week 2 lecture before we transition over to aerial photos?
So how much of this will be gonna the exam?
All of it.
Do we have a cheat sheet?
I'm with you.
Yes, I'll have there'll be a week study period leading up. I'll have like a practice document for you. You'll have a pretty good idea of what's going to be on it before you ever get the test. Not all of this is going to be on the midterm, as you can imagine. If I put all of the material that were covered in this textbook and the slides, we would be here for years. All right. Give you a second to get your lecture 3 slides open and a second for me to find them here. So we're gonna take a break from the EMR physics light sort of talk. And we're gonna get into a little bit of a different concept today. It's a little more relaxed and laid back. What we're gonna talk about today is some of like how we diagram the scenes that we're capturing. So we'll see like a photography setup for an aerial remote sensing mission. We'll see like how we compare the sensor location to what's actually on the ground and those sorts of things. So we'll see some of the old technology that used to be applied in multispectral remote sensing. And then we'll get into some concepts of photogrammetry. Anybody know what photogrammetry is?
Sure.
What?
I said I should, because.
Yeah.
Study of like how the photo is taken and like that's the interworkings of the actual like photo being taken.
The study of how the photo is taken. Photogrammetry. So, for those of you who don't know, photogrammetry is the process of making geometric sense of an image. So we are measuring geometry associated with features that were captured in our image. And like I said, there's kind of some weird, I guess, spatial phenomena that that give us the ability to actually do this pretty directly from our images. I saw this applied in a commercial not too long ago. Was it a commercial? Two people were trying to figure out the height of an object based on its shadow. And they had a picture. And we'll learn that today, how that's done. So if you haven't seen aerial photos, this is an example of an aerial photo, an oblique aerial photo. Anybody know what oblique is about this, or what makes it oblique?
I was typing from not another direction.
Not, well, not, what was that word you said?
Another.
Nadir? Yep. What is that? Can you explain that to everybody?
It's like from 90 degrees angle vertical.
Yeah. So we'll run into this word nadir, N-A-D-I-R. I don't even know if I'm pronouncing it correctly. Nadir just means straight down. So if you are, this is off nadir or oblique. If we were over top of this scene looking straight down, we would be at nadir. Does anybody know what this is a picture of? Well, do you see what is featured there? River, water, landslide. Yes. So this is out in Washington. This is the Oso landslide that happened back in like, I think it was 2014, somewhere around there. Yeah. Yep. Yeah, this was going on while I was getting my master's degree and was part of a project that I did during that time. Something that is just amazing, but they captured a bunch of aerial photos after the fact. So if the last image was oblique off nadir, this is a image captured nadir. So this is straight down from our center. This is where I used to live up in Fargo, North Dakota. This is an image from 1939. So old aerial imagery.
Does the NADR stand for, is it an acronym or is it an actual word?
No, it's a word.
Okay.
So typically when we have an aerial image mission, we are flying our plane over the scene, capturing images in a line that are overlapping. And what's neat about these overlapping images is we can use the geometry in them to do photogrammetry. So we can figure out topography, we can come up with elevation models from photogrammetry. What I've done in photogrammetry has all been done in this program called Agisoft Metashape. So this is a scaled like stream model. It's like a 4x8 table pretty much. And you take images surrounding the item that you're wanting to model. And it uses object detection to automatically piece these images together and give you a point cloud that you can process to a DEM. So there are different forms of aerial photography and photogrammetry out there. So the concepts that we're going to talk about in terms of aerial photos, we'll talk a little bit about vantage points, and then we'll look at some of the technology side.
I have a question.
Yeah.
So when you're saying aerial photography, do you mean by plane, not by satellite? Or do you
Correct,
mean
yep.
above the ground versus handheld on the ground?
Yeah. So the major difference there being there are many layers of atmosphere in between a satellite and the Earth, where there are not as many between a plane and the surface of the Earth.
But like these angles and things you're showing here, are they still applicable to a satellite?
Yes, yeah, and especially anymore with a lot of the commercial satellites or even some of the like governmental satellites, you can have oblique views now too. So you get a lot of the same looking images now from space that we used to see by plane. So when we diagram an image capture from a plane, we have our scene being the area on the ground that we are investigating. We've got a principal point, which is at the center of the image. So the principal point is going to be there for this one. You've got your altitude. Altitude is height above the ground. It's not elevation. Elevation is tied to the ground. And we've got our field of view, which is related to the type of camera or sensor that you have. So the optical axis is the shortest distance from the ground to our sensor. And then we get oblique. This is an example of a low oblique image. So in the low oblique, the horizon is typically not shown in the photograph. So here we can see that we've got offset from our 90-degree. Our optical axis is offset to be the center of the photograph. Field of view remains constant, but because we're offset, we're viewing a wider swath on the ground because of our oblique angle. And then we've got our high oblique aerial photo. So in these, we can see the horizon. We can see a lot more of the ground as well. And again, we're off nadir. Some other examples, the same can be said for drone photos. So we've got one taken at nadir and some obliques. So we've got two showing the horizon, meaning high oblique, and one not showing the horizon, so low oblique. Which brings us to a comparison of our own anatomy versus the technology that we apply here. They're actually quite similar. At the top, you see an eyeball. Of course, with the lens being the retina, the iris. And our images, most importantly, are projected to our retina upside down, just like a camera does. On the camera, we have a lens. There's typically a shutter that allows light in. Be thought of as our eyelid. Luckily, our eyes are open most of the time, whereas a camera, the shutter is usually closed. The aperture being located at the front of the camera as well. Our image, notice we have film here at the back of the camera. We don't have film at the back of our eye. We do our processing on the fly. So the f-stop for a camera is the ratio of focal length to aperture opening. So the focal length, oh, was that on the last one? Did I miss that? Yes, so it's tucked down here at the bottom below our zoom controls. So the focal length is the distance between the lens or the aperture and the film. And that's important for understanding the pixel size and the relationship to what is actually on the ground. So the f-stop is the ratio of the focal length to the aperture opening. So it'll be a distance divided by another distance. So here, our lens, our film would be, say, like down here off the bottom. So we take the distance to our film divided by the diameter of our opening. These being the typical apertures or aperture sizes. So the field of view it's represented typically by an angle. And it describes what we can see with our camera. So again, we see Nadir here, we've got our image center. And the field of view, typical field of view is say like 30 degrees. And we're not expressing this in any half of an angle. That's the entire field when we express that. So we can also express it vertically, where this is looking, say the plane is flying right at us. The horizontal field of view can be different than what is known as the vertical field of view. So horizontal is just expressed laterally from where the plane's current position. So if my arms are the wings, like my legs could be the field of view of my camera. We can also do this vertically, so that would be in the direction that the plane is moving, or in the direction that our sensor is moving. So to just quickly go over, because this is obviously old, we don't typically files, well, I don't know, I don't know how the NGA operates. Typically, we work in digital files. I know the NGA does that as well, but I also know that they do still use paper images or printed images as well. So when you print images, there is a lot of metadata that can be stored directly around the image border, which helps for the interpretation of any features from these images. So we've got things like the grayscale, so expressing all the colors that are appearing in the image. You've got a notepad for any interpreters. There's the altimeter, so you know the height or the length. That's important because if we know the altitude, we can calculate the area based on our field of view. Oh, so there are fiducial marks, so we know how to stitch these together with other images. Oh, sorry. There's a time, the clock there. There's the the lens cone serial number. Why would it be important to get the serial number of the lens? Yep.
Maybe to be able to, like, tell, there's probably like minute differences in every lens, so.
Exactly. Yeah, because I mean, if you have a study that's going on for years and years and you have to swap camera lenses every once in a while, sometimes you can have optical artifacts in your imagery because of that. And you need to be able to track why that may have happened. So putting things like an identifier for any technology is always necessary. Because if something is awry in your remote sensing system, you need to be able to troubleshoot. And when you're troubleshooting, you got to get into the details. You've also got your focal length there. We've got our frame number, so we can see which images are nearby, and the mission name and date, and also our navigation data. Not sure what they mean by navigation data because there is nothing here.
So how do the fiducial marks work, the little plus signs?
Yeah. So typically there will be images that are, well, if they're taken for photogrammetry, they'll be overlying by 60% area. So the fiducials can be associated with pixels on the neighboring image or with a geographic location on the ground. That makes sense?
So it makes sense if you try to align two images, like if you take two screenshots of Google Earth and you can line up the roads and intersections and such.
Yeah.
I guess I'm just curious as to, is there something magic about where that the plus is, or is it just to reference to the next frame that might be one over?
Correct.
Okay.
Yeah, so
You would assign like an XY coordinates on the next frame over, or pixel coordinates.
yeah. So if you were to lay these out on a table, it would help you lay them out on a table quickly and neatly. But I mean, if we were to scan this into a computer, which is typically what would happen, we can then associate XYZ locations with our fiducials rather than having a bunch of georeferencing points out in the image. It makes it a little bit easier. Any other questions? So looking back in time, this is an example of a multi-spec setup from the 1950s. This is like post-World War II technology. So on here, each of these cameras are handling a different band. So we've got four cameras. One is an infrared camera, and the others are handling red, green, and blue independently. More modern systems, this one being mounted in the bottom of a plane. There's typically a pretty large film magazine associated with these. If you go digital, there will be processing computers, data handling computers there. There's obviously a CPU for this and some different mounting structures. And the camera is actually sitting under this big film canister here. So the camera is this gray box at the base. So Isaac Newton first started experimenting with light back in the 1600s. He started by splitting white light and then merging it back into white light. And he discovered that these different, the different spectral components of light all correlated to different wavelength EMR. He even published a book later on in his career. Lovely image. So getting into a little bit about, we talked about reflection and transmission and like why things appear certain colors. So what happens when some, say, we can have certain objects that that only reflect certain colors or certain wavelength or frequency EMR. So like an object that appears red absorbs all the green and blue light and therefore appears red for that reason. We can also have filters, which are common in our sensors. So say for a camera that was collecting only the green band, we could have a filter in our sensor that would absorb all the other colors and only allow through the green light to our sensor. So we can have like a reflector method of doing that, and we can also have a filter method of doing that. So transitioning over to photogrammetry, we're going to be talking some different geometric aspects of aerial photos. And like I said, we'll get into measuring target height. I've even got a little math problem for you as well. So the idea is here that we have overlapping photos. So the line at the top is our flight line. The exposure stations, these represent where different pictures are taken. Importantly, we know the height, the altitude of our sensor. And these images have 60% overlap. You need this for photogrammetry. So in each of these, the coverage of the photograph is represented by the intersection of the lines with our theoretical terrain there. And from these three photos, we can also see that we have one area here that is overlapped by all three pictures. There are methods of doing photogrammetry with only 2 photographic points, but 3 are the preferred. So you can kind of get the idea that this can be challenging to line up in an aerial survey. So a lot of times oblique angles will be captured in between flight lines as a way to get that 60% overlap for all of your images. So when you capture an image, we've got our principal points. And we're going to start overlapping them down here. So keeping track of our principal points, our line of flight being in that direction. We can see we have 60% overlap of our stereoscopic model. We'll talk about stereoscopic models and stereoscopes here in a second. And then from this, from the principal points, we can come up with what are called conjugate principal points. It's essentially taking the principal point from our second image and plotting it on our first. So we're correlating points in space. So when you capture an aerial image, you've got your exposure station L, which is a given height or altitude above sea level. You've got your focal length, the distance between your film, your negative being the image as it's projected onto your film. Is everybody familiar with that? Negative. I know like film isn't really common anymore. It'd be weird to try and explain that to somebody who only knows digital photography. So the distance between your negative or your film and the exposure station L is your focal length. Of course, we're tying this to the corners of our images, A, B, C, D, and what's on the ground. So this is your image. This is actually what's on the ground down here. You've got your principal point, PP. That's designated as O in your image. You pick a positive Y, a positive X direction. So we can reference all these. And just a quick simplification of it for 2 dimensions. All the same features on there. Any questions about this?
When you hire a company to do this, I'm assuming they're gonna deliver the product already stitched together, right? Like digitally.
A lot of
digitally
times it
stitched,
depends.
Really,
Yeah.
I would pay extra.
Yes, yeah, and you usually can.
Yeah.
Yes, for all the referencing to be done ahead of times. Yeah, no, it's a big part of it because you either have to go reference the images based on the known location of other things in your images, which requires a GPS a lot of times, or a lot of computer work. Or nowadays, like in drone remote sensing, we actually know the GPS location of the camera. So sometimes it's nice and easy if you have a GPS enabled camera or a drone that can process that information for you on the fly. It just, so getting your images in the right location and correcting them is that's like half the work. Some people dedicate entire careers just to like the pre-processing part of this.
Well, and then they are the ones that turn around and sell it to people like us who don't want to do it.
Yeah. That's, me being a scientist, like I just want to use the data products. Like I want to get to like a usable scientific product. And that's not like on the correction side of things. Penny?
Once you're past a certain altitude, does the curvature of the Earth start to matter and complicate this?
It only for really big images. So like even when you get an image from a satellite, the image isn't big enough to have to start dealing with curvature. But when you take it into a projected coordinate system in GIS, that'll account for curvature too. But yeah, so it would be even smaller issue if you considered like a drone image. Yeah. Any other questions?
would be important? I know it's one of the factors, but I don't know why it is.
Curvature,
Temperature?
temperature.
Yeah.
For,
Is that
for
what-
what?
It's what Henning asked, right?
Wait, were you asking
You said
temperature?
Curvature, curvature in the earth.
Okay, sorry.
Yeah,
Well, the camera probably cares what temperature it is.
yeah, definitely.
Can't
Yeah.
handle it too high.
Well, I mean, you could also be collecting thermal imagery.
No, well, yeah. Not the satellite though. Is that,
Infrared? Get it thermal. All right. So the whole idea of this is that from our scene, we're gonna be able to measure the size of objects both in our image and in the real world. So we want to know this. And we're gonna do this from measurements in inches. So we're gonna take a couple measurements from our photo. And we're gonna try and get at the actual measurements that correlate with these features on the ground. And if we can reduce our error as much as possible through all of our pre-processing and making sure our images are placed correctly, we're hoping we can get rid of any errors, or we can at least understand where the errors are coming from. This gets a little more complicated when we're dealing with complex terrain. Because the altitude for all of these different features are different. This is where it is important to have a digital elevation model. For flat terrain, like where I used to live up on the prairie in Fargo, flat as can be. And I move here and there's hills everywhere. So when you have hills in your scenes, or hills or mountains or anything with relief, it's important that we have a digital elevation model so we can correct for all of these different values of H across our image. All right, so now transitioning over to our little fun activity for the day. Trying to measure height of an object based on an image. So that starts by selecting a principal point in the image. And the point in the image, a lot of times is the center. So that's what we're going to be dealing with today. And then we have to pick a building. It's best to focus on a corner of a building. That way we can just measure the length of the side rather than some area in the middle. So for this, we're selecting a point right here. We're measuring the distance R between that point and our principal point at the center of the image. And we're measuring D, which is the length on your image that represents the height of the building.
And principal point is.
It's a reference
it's
point.
Usually the center of the image, but we want it to be the most nadir point, right? Of the
Correct,
image.
yep.
Okay, it is usually the center.
And yes, yeah, so if you're taking a nadir image, the point that is straight down will always be the
That's
principal
nadir,
point.
And that's where it's,
Yeah.
okay.
Okay. So what we just did was get R and D from our image. And what we don't know right now is H. The distance between our sensor, our exposure station L, and the ground. So this is our relationship. So the height of our building is going to be correlated, well, sorry, the height of our building in real life, IRL. Not that old. It's correlated with H, which is the height of the building in our image. Or sorry, I'm mixing this up. Big H is the distance from the ground to our center. There we go. So big H is the altitude of our sensor. Little h is the height of the building. That's what we want. And D and R, as we just saw, R being the distance between our principal point and the point we're measuring at the top corner of our building. And D is the length on our image that is correlated with the height of that building. Disregard those numbers for right now. So this uses an optical artifact known as relief displacement. And this causes objects in an image to kind of lean outward when they're off nadir. So our example image there, we've got two smokestacks that are in the center of the image and two that are out towards one of the edges of our image. And the smokestacks that are higher up in our image towards the edge are apparently leaning. They're not really leaning. They're just leaning in reference to our camera location. And I mean, we don't really want this in our images because as pictured here, the spatial locations correlated to those smokestacks are off. So we have to correct. But we can use this artifact to our benefit as well. Which brings us to a little applied practice for you. So take like 10 minutes here, and I want you to calculate the height of the tower in our applied question here. So I give you measurements for the image, the displacement, and the radial distance of the tower in your image. And I also give you the flying height for our sensor. So we're going to do this and call this our like 10-minute break. So in 15 minutes, so at 5:30, let's come back and we'll share answers. And then we'll wrap up the rest of lecture for the day. Sound good? Yeah. Is that general agreements?
Trying to look at it.
Oh, well, neither. I'm gonna go get my water.
Maybe turn it sideways.
Cells. Central Texas. Surface drops or scallops. Oh, there's no bone. It's like for us, it's like this forecast there, the use. Yes, it's 500. This is awesome. The best piece of it. So like you're trying to match the best pieces we have now. That's central. This was like, this is the next step.
Surface based. Hold it. This is just over the house, but this is the mean. We got one mass per supposed to two. So the side of that nice color, just still over. So we're definitely like 1,000. So pretty much. Post funds more, there's no cake. It's for everyone that. Now, I mean, so like. Oh, here. The tornado part. Something else that will not let me. It's like starts next southwest. Southwestern, not really good for training. If your winds were like from your service winds were from this way, or even at 50, get some cell ingestion and training up. But
A few days, like really yesterday.
yeah, we had it
Coming this way, is that like 11?
I think that was very good.
So I'm just gonna front which is like.
Some tropical system. Circulating this way, you can see if they're.
Oh, yeah.
Ridge. Yesterday. We were kind of. It was pretty easy. I went throughout the day today. And I made this trough one bit. You look at the weather. Yeah.
The one that, last night.
That's what he was asking. Last night was actually.
Okay.
The pressure goes, or the winds go from high to low, so they're.
Right. I noticed it was coming from a weird direction.
Yeah, it was a super weird direction. So they're like, there's like this extra tropical system that's kind of merging into the East Coast, but. So like the southeasterly, they kind of start over us. Go up. Like cloud top temperature, so like the colder it is, the taller the birds.
Color's cold.
So like the redder is the colder.
Okay, okay. No, I was kind of wondering that.
Yeah. So like yesterday, yeah, nothing too crazy. Those like weren't very severe.
Do they have, is there, like metadata for these?
Yeah, there is.
Okay, nice.
University of Wisconsin. They have the cooperative thing for like satellites.
A double lab that's there.
Yeah, they also
Yeah.
have the lightning lab.
Okay, okay.
But then today, there's like cold front, there's like a red. Like that's associated with like severe.
Okay.
Oh, sweet. A lot colder tops. Yeah.
That's cool.
So Florida should be like after this.
Alright. Exciting.
That data college page. Yeah. Is that all open source? Yeah, yeah, it's all open source, all weather data.
Alrighty, folks.
That website's super.
Is it okay if I call you folks? I know some of you aren't probably folks.
Really? That's awesome.
People,
That's funny.
humans. So what's the height of our tower? Yep, 43.46 watts.
Meters?
Meters, yep, meters. Yes. It's a functional. As I mentioned, we can also use shadows to do the same sort of thing, just using trigonometry this time. So everybody should know SOHCAHTOA by now. Go back to high school geometry, SOHCAHTOA.
That was like 23 years ago.
Well, you're in luck because it's not going to be on the exam for you to
All
know
right.
that. SOHCAHTOA is just a way of remembering spatial relationships between sides of a triangle and angles. There you go.
Okay.
My high level description. So here and using shadows, the shadow being represented by our big arrow here. The shadow has a length L. And if we make this a triangle, that meant the L makes up the adjacent side of our triangle and SOHCAHTOA. And the opposite is given by the height. So if we know the angle of the sun's rays shining on our scene, we can come up with the height for an object by taking the tangent of our angle and multiplying that by L, which is the length of the shadow. So the example here gives us two shadows. The length of the shadow on the image is given in inches there, and the corresponding height of the object, in this case, a parking garage and looks like an apartment building to me, being what we're measuring. So we mentioned stereoscopic analysis. Essentially, that means we're just analyzing 2D images in 3 dimensions. So this is a stereoscope. And I am 32 years old, and I'm old enough to have learned my image analysis on these. So when I went out to field camp as part of my undergraduate curriculum, we broke out stereoscopes And we were measuring the elevation of some of the peaks that we were going to hike out to that day and do our geologic mapping. Yeah, so people usually make maps with like GPS. We were making maps based on the location of things in the distance. So we learned all, I mean, off, what do they call it? Yeah, off grid or off, backcountry. Backcountry is, yes, that's the word I'm looking for. Learned all the backcountry methods for navigating, determining like your elevation at any point on a map. This is one of the methods that we used. So the idea is that you have your stereoscopic pair of images. So these images having 60% overlap can be aligned next to one another. So that you see in 3 dimensions, essentially, when you look through your stereoscopic lens. This is the same way that we make paper images seem 3-dimensional nowadays. You know how you put the red and blue filters on your eyes? Well, they print stereoscopic lines on those images in red and blue that give you the optical effect of looking through these. So there's really 2 images printed, one in red, one in blue. And it's the same thing happens here as when you're, say, looking at your like 3D comic book or whatever. And this little thing right here is your parallax bar. And that is for measuring things in your images. So you can quickly come up with a estimate for R and D in your image. And of course, you know H from your aerial survey. So you can quickly measure the height of objects in your image using a stereoscope and parallax bar. New method of doing this is more of a joke than anything, is to drop a point on Google Earth. We take 3D building data now, and it is all part of the data that are stored in Google Earth. So you can go drop a point, calculate the height of your building. You can also, in Google Earth, use shadows. So you can measure the length of your shadow. If you know theta, which on some of these buildings, you can kind of come up with a estimate for it.
I meant to ask earlier on the shadows,
Yeah.
do you basically just know the angle by the time of day the picture was taken?
Yes, yeah, I mean, to give you a simple answer, it's really, I mean, it's complex to figure out the actual angle of the sun in relation to something else. That being said, there are like all-encompassing tools to do it. Say like, oh, I know ArcGIS Pro has a tool that can calculate the like sunlight exposure over, even they can do it over a variable period of time throughout the year too. Yeah, no. So yeah, it's all been calculated. You can usually, for any period of day at any location around the earth, you can go get that number. It's not like you're going to, say if you were doing a drone survey, you weren't going to survey the angle to the sun. You're not going to do that. That's the theta there is going to come from a plug and chug calculation a lot of times based on the time of day and the location that your image is covering. So the whole idea behind doing this is to extract building heights. So this is a 3D model of SLU's campus. I want to say this was made back in the 90s. You can do the same exact sort of thing using more modern technology called LiDAR. LiDAR being another form of aerial remote sensing. And it even does the same sort of thing. It makes a point cloud. So another example of building height models extruded to become 3D models of buildings. In reality, nowadays, to show you some, it's going to tell me to switch browsers, isn't it? Modern examples of photogrammetry are a little more appealing to look at rather than just extruded building models. So these are just some examples. Some people like to focus their lives around creating 3D models. It's typically a pretty appealing lifestyle because you have to go out and fly drones around historic locations, say like this castle here. But yeah, in artifact preservation, it is a pretty neat piece of technology to rely on, and it goes a lot deeper than just extracting building height from. So what we're touching on today is just basic. Yes, Henning?
So Google Earth, that does have like trees and buildings and such, is that all based on photogrammetry? So they can do it for everywhere, basically?
That's a great question. I don't know if they use LiDAR building extractions or photogrammetry.
Maybe depending on the locations.
Possibly, yeah, and the availability of LiDAR data. My thought is they would probably use LiDAR because it's pretty simple processing to get buildings from LiDAR data. It's a little more tedious and time consuming if you need aerial surveys.
So they use LiDAR data and superimpose the RGB back on the surfaces?
Well, oh, that's a great question. Because LiDAR data has RGB tied to it, but they're not using that imagery for the buildings. But that being said, how do you get the side of a building from an image that is nadir directly over top of something?
Yeah.
So my guess is they would probably stitch like an oblique view with the nadir views to get the side details of the building and build it that way. You should take data visualization, Henning. We get into some 3D building modeling in there. We use the LiDAR methodology though. Everybody here should take geovisualization in the spring. It's a fun class. So these models are here to inspire you to get into photogrammetry. Photogrammetry is really fun. It's really easy. I do it. I used to use it just as a reason to get out and hike. I'd go monitor a bluff. I'd take pictures of a bluff while I was hiking and build 3D models and compare them over time.
How good of a camera?
You can do it with the cell phone camera. The most important thing is the GPS location.
Like make sure you know where you're taking each photo.
Yep. Yeah, so you either need to know the location of your camera or you need points on the ground that are referenced. So you need to either know location of objects in your images or the location from where your images are being taken. I believe this wraps us up today. We're going over to lab 2 now. And this is kind of a self-guided thing this week. Last week, I guided you through Envy. This week, I have instructions for you and a walkthrough. Is that a hand?
Yes.
Yes.
Do we have to use ArcMap or can we use ArcPro?
I know it says you're going to be using ArcMap on there. I don't see any area that you need to use ArcMap for. ArcGIS Pro is fine. That being said, yeah. So what you're going to be doing here in lab 2 is some pre-processing. So we're working up to processing imagery. So we're going to do what we call a radiometric correction for radiance today. also known as a radiance correction. We're gonna do a dark spot removal, and we're gonna do a geometric correction. And the idea behind doing all this is that we're standardizing our images across time and space. Because images of different locations taken at different times can have all kinds of different lighting conditions. So this makes sure that we can compare things or images taken at different times and in different locations. So that wraps up me talking for the day. I will point you to our week 3 module here, where I've got everything organized for you. So I've got a PDF. This is straight from the NV training modules. And the data that you will be using are the WV-2, stands for worldview 2 data.zip. So you can go ahead and download these. Make sure you're managing your data smartly. So put it in a good location that you can take home with you if you need to. And then you can get working on this here. It should be pretty straightforward. It tells you details like where to click, what exactly like clicking in a certain location does. We've got some background, which I've already kind of explained today. Oh, and under our tasks document, because I know people are going to be like, what the hell do you want me to turn in? It's the most common question I get. I'm looking for a zipped folder. So you're doing 3 things in this. You have a radiometric calibration. So that's going to create 1 image. It's going to ask you to give it this name. So I expect to see that image. You're going to do a dark object subtraction. I need to see the product of that. And then I also need to see your geometrically corrected image as well. So 3 things. If those things are in there, you'll get full credit. The rest of the time is yours. Heading, were you able to catch up from last week?
100% yet.
Well, let me know if you need any quick intro to like NV sort of things. Yep. Is that a hand up?
Yeah.
Oh, okay. What do you mean samples? Oh, you're looking for like the sample data? Yeah. So if you follow like a file path like this, so it's usually the C drive and the program files, IntroRS. It can be any image. You could go get one. Yeah, that's fine. Yep. Yeah, and that, I mean, that might just be because we're like campus, which I don't know why it's. What's up? When I was at in our So I don't know. Something. But that's fine. Okay, okay. Yeah. Well, yeah, totally. And I mean, I think you probably even know from past classes how to like go get satellite photos online too. So that's been fun. Yeah, yeah, exactly. So anything is fine.
But I just couldn't.
I know, yeah, well, I had the problem, it's like I clicked like all the way down here and then I would see examples and I would just go to examples first and then I was like, where's the deep learning stuff that I was seeing before? But like, yeah, and so all of these are just different folders with different example data. Many of these will work.
How about if I just like do one, like, but this is that.
What do you mean? Well, you know what all these are, right?
Yeah.
So I mean, it's not really, these are all just vector. Oh, I mean like,
Yeah.
yeah, some images are gigantic. I was in deep learning, it's the one I was working on. Yeah, just make sure you get any supporting files too. So like, if you wanted like this label raster containers, do EGR and that. One's the header for NB, the other is the actual file. Yes, yep. Well, there's well, two, there's a DAT and an HDR for one, and then there's a second photo. So kind of like a shape file. The shape files have like 6 different files. Yeah, there's only one file that actually holds the data.
Output directory for the preferences, it's asking to set up.
You don't have to. It's so if you do set the default, it'll make your life a little bit easier. So there you
But,
go.
just for this example, to
Yep.
find out the, do I just use the encompassing lat2 data for the input directory for this, or I know. for
Yeah,
this,
yeah,
this,
yeah,
this,
that's
this.
totally fine. Yep. And so for the input directory, I usually like to go one file folder higher than I think I go to. Because that's just gonna default, that's the default folder. that I'm looking in for data. Yep. Oh my gosh. Are there any other, you got any other windows open? All right, try plugging them.
Yeah.
Control, delete it. Let me know if that fixes your problem.
Okay.
Fingers crossed that it will, but
Yeah.
it keeps freezing there.
I do not know.
Okay, that might be-
Yeah, I have bachelor. My ND won't open.
Okay, let me figure out that licensing code again.
You have to.
I just emailed it to you. I can show you where to enter it.
Looks like I have all this stuff.
Yeah, it's just not licensed.
Okay.
It's no problem. So copy that. And go search down in your search bar over there for Harris. That's it, Harris License Administrator.
That's where it says.
There we go. Activate local.
Yeah.
Paste it in there.
Oh, I'm in a different.
How did I
Okay,
get
so
public ethics?
it's hidden.
I don't
so you have to
remember
go
where to go. Thanks.
Wait, so
Oh, that's fine.
oh, wait, we're doing two different things. Are you changing your preferences?
Cool, activate succeeded.
Set the
Close it.
downloads to directory.
Should be good to go now.
Preferences.
I'll make sure it's gonna start up right. This is when it would do it, right?
Yeah.
When you try to open something.
It wouldn't even show me this.
Okay.
It was working last time. It's weird.
Yeah, I don't understand it really. All right, cool.
Do we have to do it? I can't find this data. Install the FFP course files.
Oh, are you talking about the file paths that they show in the,
Preferences, yeah.
so, all right, a little bit different from what they've got diagrammed, because I share all the data that they're referencing. So everything that is referenced in that file location in your, in the document is in the lap2 WV2 data folder.
Okay.
So don't pay attention to that file path.
Okay.
And just go to the files that you downloaded.
So you,
So for input directory, you can just put literally the. I was trying to find where to save my file. Download the zip to.
Yep, yeah. So that way, if you save your session in NV, it'll save your JSON there. It'll save any outputs. If you set the output location. And I even give you an NV out folder here.
But that's for the outputs. no?
Yes, yep.
So what do you use as the default input?
Well, that's just pointing to a folder. So that's gonna be where it's gonna start looking for files when you hit open. This is a minor background detail more than anything. Don't get hung up on setting the default input folder. Yes, sir.
So when we put it in for like the final image into like a folder, can we just do the DAT file or do we need to include like the ENP and HDR files?
You'll need the supporting.
Okay.
Yeah.
Okay, just want to make sure.
Yeah. So the way that I would handle this if I were you is I would extract everything in this zipped folder and then don't move it anywhere. You can take that whole folder, take it to your drive, you can take it home with you. Just don't move any individual files within the folder. And that's because a single one of these files has a number of supporting files. And the most common thing that I see in classes like this and Intro to GIS is people only sharing one part of their files. So if you do move, say this TIFF image here, you need to make sure that you're grabbing everything with the same file name as our actual image. You got that? So it's easiest to just download the zip folder, extract everything, and work right out of here. So when it asks you to set your output folder, I would point it to this one, this NV out. I know what files to look for, but it would make my life a lot easier if they're all in the same place, nice and organized. Yes.
So, you are into to the dark object subtractions from the image I have got the first one, or
No, don't worry about turning in the original image. Is that what you're asking?
no, I'm asking that I have done the first part.
Oh,
Now I need to do the dark object subtraction.
yeah.
So what image should I use? The first one or the processing?
Oh, does it not tell you specifically which? I thought it told it had you use the corrected image.
Yeah,
I'm so confused.
I know that. But I cannot find the dark object.
So you've done the first part, right?
Digital quote. Optical sensors, digital quote. Optical sensors. Digital quote. Yeah.
It says to use the calculated image. What about the word?
So use the corrected image,
Okay.
the calibrated image from step one.
I just opened.
Are you saying it, Mama?
Or,
Oh, geez.
It might just be organized differently.
Ooh, thank, I can't even get the freaking thing open. This is gonna be a fun class.
It might not have it.
Just the thing. That's for the NV, no, that's like the NV. And then everything.
Yeah.
Yeah.
Probably in what menus we're seeing right here. So let's see.
There's the start.
I bet you. You extracted. Oh. Desktop.
oh, just the same image.
Yeah. Yeah.
So why?
All the classes that we did.
Oh, because I don't.
Yeah.
So, yeah, that's kind of. Explains. more.
Yeah.
I have a question.
Yep.
So I'm trying to do the second dark solid action.
Yeah, yeah.
So I'm not sure I should use this region.
Do you have a region of interest?
File that you just created, that's right. Exactly. Just read it, rename it, yeah, whatever, yeah.
Oh, yep, I forgot.
Yeah.
That'll get you there.
Yes. Go into the X one.
Yeah, this is true.
It's dark. Using the new caliber.
Okay.
It's really weird.
Yeah, so when I do
Yeah,
that,
we're gonna have lecture.
I'll
with
just
them.
give you your, I mean, so I'm done working. We close Envy, everything. So what I would do is take this being your work folder, so everything is happening in here. Zip it up, so right click, send to zip folder, and then once it's compressed, I can drag it and drop it. So if you have a flash drive,
But I know
Sometimes I just send it.
Lizzie tested
okay, so
negative.
you can do that with that. So zip folder,
Garrett tested
you can
negative.
attach to an email. Or
Maggie's
upload
tested
to a
negative.
Google Drive or
Max tested
OneDrive.
negative. Pretty much, so how it works is he called them on Saturday.
Let's get out. Like, so,
It was
oh, yeah.
hour and a half long phone call.
Yeah, about a little bit contractors on this. And
And
it's
then they
kind
called
of weird.
everybody else.
Yeah,
Like Max got called.
so under save as here, they've got
Maggie, I
this
think I
save
called.
as
Lizzie
NB
might have
and
didn't
TF,
call me.
GIFF.
I'm like, okay, I was waiting all day on
And
Saturday
this
for a
is
phone
what
call, they
you-
never called. me.
so
Okay.
This isn't even,
I guess I'm
so, I
fine,
mean,
but nobody,
it's
everybody
not
else is
like
negative. so-
GIS where you do a bunch of mapping
It's
and
like
like
over.
map objects and stuff. A lot of times, like when you create the JSON file for this, it's just like 3 files. So when you do a processing procedure, it's saving and outputting the file. So it's, I mean, there's not much to save when you do save in the session. But this is how you do it, and we can.
Oh, Zoom.
Yeah, I bet.
Because I know those pipes.
There's all the files in the
Yeah,
lab.
yeah, so you just point that, I wanna see what this looks like again.
What we means into this. That's a.
Yeah, yeah. It looks like it just saved as an image.
Yeah.
So tomorrow,
I thought that I actually did. The tool, right? And then the ROI with the plus. It's under this section. Oh, so I did this. Did you go up
This is-
to?
yeah, so this is-
bar?
Right,
right.
up here.
The plus over our line.
Yep.
It's a lot easier to understand. As you start.
This reminds me, I took IntroRS, and this is pretty much more.
Oh, yeah, I mean, that's.
That class is so.
With him.
IntroRS, like 40-10 or something. Classes. Like they have a big song.
So we should have 2.
Yeah.
So there you go. There are 2 images. Yeah, save or NV session is the one. Yeah, no problem. A quick little logistical point, I guess. I'm gonna show you how to save. So from what you're doing right now, in the upper left-hand corner, file, NV session. Everybody get that? You see that save button there? So that is what you use when you want to pick up from where you left off later on. When you go through that save dialog, you'll put that in your folder location, wherever that may be. And then when you get back into NV, you can just go to File, Open, and navigate to that file and click it, and it'll open up whatever you had open on your screen before. That being said, if you mess something up, don't freak out. When you do any procedure in Envy, like anything in the toolbox over here that we're doing today, you are writing an image file when you run those procedures. So there's nothing that you need to save later on. So you actually have all the work that you do. The only thing that is being saved by Envy when you save your session is the list of what is open in Envy. So you already have all the work done. Just don't get concerned if it's not showing up on your user interface. It's still there. Unless you physically delete it. I can't do anything about that. How's it going?
Good so far, but when I got to the directories, I'm not finding, and I downloaded the data, I just kept it in the download section. It said,
Perfect. Yep.
But when I went to out the directory, I didn't get anything specific beyond.
That's fine.
Okay.
So for the input directory, it looks to me like you are one level two.
When's the
level,
deadline?
Okay.
Because that's looking in your output.
The deadline.
For your
Oh,
input.
okay, okay.
Yeah.
You
That's all.
can still,
I just stayed there.
you can
So-
withdraw and it won't
so
affect
just
your.
data's just
Yep,
that.
that's perfect.
Oh,
You can
yeah.
withdraw. It
So
won't-
the idea is now when you open a tool.
It's very straightforward. And once you get past
We didn't
the,
even open it.
I know, once you get past the file bullshit, it gets easier.
I could open this without the
Sorry.
computer.
It's
Yeah.
like,
The tutorial will give you like literally word for word what you need.
Right, right. It looks like they've updated their list because the walkthrough is.
Oh, yeah.
So you can open it, a TIFF is a stable format for an image. So you can just use open there rather than the open as menu.
And then also.
And then boom, okay, and the one that you want is that actual TIFF, so the one with the little icon.
Right here.
Okay.
Do you not have it open?
I have one, but I don't have.
One tip I'll give you.
So you haven't had any issues getting started?
So
Yeah, honestly, my biggest problem has been being just
Yeah, he showed me how to open that one, but
Yeah, yeah.
I don't know what to do. I have no idea.
Yeah, yeah. Okay.
like.
You're not.
Completely different language.
Yeah. But I'm getting the hang of it.
Good. I'm trying to get better at teaching people on how to manage data too.
You could-
It's not really.
Right.
I don't know how to do it all.
Connor, why are you looking so dapper?
Just like give you
That's so silly. I don't know.
Okay.
And I didn't know how long class was, and I know like it was supposed to start at 6, so I'm just headed directly different like channels.
But isn't that what?
Well,
I'm
we're
paying
done for the
for?
evening if you two want to go.
Oh, no, I'd rather get this done.
Okay.
Yeah, he'll help you.
Whatever you ask. Let's put this together. I think you get this. And you can't get the money even if you drop it. So when you start typing, it will show up here.
Okay.
So once you put this in, it gives you this window. Next step is when you are. Let me just- This one's like in the file. This is the website. So like this is the only thing that we selected, so this is the same thing. Yeah. So now it's step 6. I'm slowly, yeah, I'm.
Oh. Yeah. Right,
I think I'm just gonna.
down. Shit crunch.
Oh. And then I tried to change the file thing. And then I clicked it too many times and then it just freezes.
Yeah.
I have shadows.
Those are definitely shadows. I think this might be like half shadow.
I just saw that and I was like, oh.
Yeah. So I think you got half the shadow there. It looks like it's like this side is shadow. I don't know if this side polygon's not shadow though. It's like that is all shadow. I think. Move it this way. You see like the edge of the shadow? Like here? Move it as close to my finger. Yeah. Yep. That's good. Yep. It's all shadow. trust your ability to interpret shadows.
You look at the image and they're very
No,
similar.
you did it right.
They're very similar.
Yeah, I know. And I mean, some of the corrections are the same way, like you make a
Yeah,
minute difference in the way the image looks. So it's like, how the hell did this work? So yeah, you should see your dark areas get lighter, essentially,
In the
in the corrected image.
radiometric calibration.
In the radiometric calibration, you should generally see your whole image get a little more clearly displayed.
Correct. So in my subtraction image, that's the one that.
That's the one that you'll see the shadows will get lighter. And so what you're doing when you're creating those areas within the dark areas, within the shadows, you're measuring the spectral distribution in those areas. So you're gonna enhance, you're gonna stretch the spectrum in those dark areas, and then you're gonna replace the dark areas with your stretched dark areas. So you have a bunch of dark pixels that are smashed up. We're getting statistics on those, and then we're going to enhance them so that the same colors are shown across, or I guess at a brighter part of our spectrum. So taking black, we're stretching it out to show depth, and then we're replacing the dark areas in our image with the stretch statistics that we captured from the dark areas. You get that, Camilla? You look like you're a puzzle.
This is like the building it's talking about, right? And this is my subtraction.
Zoom, way.
Sweet, sweet.
I finished that.
So now go back and forth. Let's see.
Yeah.
So if you want to do a pixel level investigation, you should do that too. So remember last week how we created those spectral plots? The curvy colored worm there. So now pick a location within our shadow. So that's looking like a 0 there, pretty black. So now we need to look at the same location for our other image. So that's for the subtraction, right? So we need to get that same spectral value for the. So you might have to close to sort of change the layer that the statistics from. So now it's just the same.
Oh, I changed that.
Let's do that. That's what we're supposed to do.
Yeah.
Make a couple shadows, try to like those two, make sure you don't get anything right. Don't mess up the calibration.
It could just be that area that's to check out the shadows. Or if you need to, you can go back and redo the dark. Yeah, because if you pick only pixels that are in like the darkest of dark areas, like it's not gonna consider these as.
Oh, so you should get a little bit of like the lighter too?
Yeah, you want variation.
I literally chose like just the darkest.
Right, no, we want a broad range of what is contained in the shadows.
But also because technically that shadow was on water, was going to a hard surface or something like that.
It's
maybe
gonna, yeah, it's different. I mean, it's just optically different.
Should you get a little bit of water and land?
Yeah, yeah.
A little bit of
Yep.
building, okay.
Yep, that, I mean, that just makes sure that we're treating all the shadows and not just the
The
darkest
picture,
shadows.
in the, like, what do you call it?
It's so much lighter,
It-
the contrast is.
Oh,
Well,
yeah.
it makes it look like they're just grabbing the tiniest little spot.
Right, right. Well, I mean, there's only so much you can show off
There's
on
only-
a little computer screen, especially in like a snippet of an image. So, I mean, they're only showing one shadow, and there's really, I mean, there's a bunch of them on our image.
I'm gonna redo my dark areas.
Okay.
Around there.
No, I don't need to see your areas of interest for that. That's fine. It just does it. Yep, the 3 images.
I just want to like turn it similar to the other.
Yeah, yeah, so the submissions they'll be tracked on there, so if you want to put it in like separate submissions,
And
you
then
can.
comment of what changes or whatever.
Yeah, you can do it that way, or if you like do a couple dark area subtractions, just give me like a 1, 2, 3 on the end, and say for the one that you want me to create, just put. Yeah. Or you could also put like the grading stuff in a separate folder in your submission folder. That'd be another way to do it. Is that a hand up? Camille?
Yeah.
All right.
I
Second.
know. Coming in there, so it's good. So. I think that's one place.
Yeah, so you don't focus on only one area. I know they only show one like place here, but we have a whole image of like variation. And they're only showing us getting
Analysis that I have to do a lot tonight.
like city water area.
Yeah, I don't have.
So, yeah, it's just this little shadowy water area, but really like we have shadows that are here on land. There are shadows that are like entirely across our image. That are over here on like the docks. So we need to get different shadows. Not just one.
What's the? Oh, okay. I just did something with the shadow.
Yeah, yeah, right. And oh, yes, so it's just saying that, so they just want us to zoom to this shadow that they're. And that's just right here. Yeah, and they're grabbing their box that's like right here. Yeah, yeah, that is, I mean, really, we always want a broad like range of variance within the shadows. So make sure you get some different shadows too, not just this really dark one.
Yeah.
And like.
Yeah.
That's what I couldn't find that in my, cause I downloaded it on.
Yeah.
So I'm just like basing it off of.
Make rectangles of dark,
Oh,
dark areas. My ROI.
it's done.
Yes.
It's completed.
Might as well stay over here.
What's up?
Oh, everything. So I changed the dark pixels, but I was doing the little, I guess. But it changed. I did the third one, it's pretty green, and now I came back to the dark pixel. Am I supposed to be making rectangles?
Oh, you
Oh,
started
there.
a new one, that's fine, so we can just. Whatever that is.
I was supposed to make rectangles.
Oh, yeah, yeah.
Okay.
Just make sure these red rectangles are. Select tool. So one thing that I see is this red rectangle is partially on, I don't know, whatever this feature is. Looks like a water treatment facility to me. So
You can see that.
this needs to be completely in the shadow. Right now I see it's getting water pixels over here on this edge of our shadow. It's getting some of this here. I mean, I can see the shadow. Just, I mean, the tiniest little variation there, but still, the computer's going to care.
Yeah.
And like this one, I see like 300 pixels.
Yeah, it wasn't zoomed in as
So there's gonna be a shadow here. But yeah, like get down to like the pixel level and make sure you're only getting pixels that are shadows.
Okay.
But otherwise, everything looks good to me, so. Why is it creating too much? Undo, what do you mean?
So, good there.
How are you able to click on it? That's what we're having. I can't select yours.
That's why I wanted to undo.
I was able to right click and delete.
Delete the message. That one.
That's what I did. And then I I know it wasn't responding earlier. I had to close it out. Maybe that's it.
Oh, okay, here we go.
Or maybe it's just me. I don't know.
User error.
Yes. I didn't notice
All
my
right, all
weakness.
right. So I want this finish. Change to purple now. There we go. All right. Now we're, okay. That's weird. So we're building the dark pixels now. All of them. So there, now you can start over fresh.
Okay,
So
story of my life, just redoing something because
Yeah.
it doesn't want to work.
welcome to grad school.
Yeah, this is fun.
Sorry. Oh, I can't give you another problem. Please, I'll wait for the marxism. Which is this one, right? Because it's so small.
Do more than one.
Okay.
So, yeah, so like zoom out and zoom into other shadows
Okay.
on your image and do like a spread of them. Were you,
So, it looks a little different.
yeah, we're like 3 versions in the future.
So that.
Oh, that's brilliant.
Yeah, default's fine. Yep. That's in Tokyo, so, yep, I've never seen 50 or 54 work before. Yep, no, that's perfect there. Yes.
So, I said some that.
Let me come around to your side.
I said some of the files in here, and some of the.
Okay. It's not, just, so if you want to move these in here, just make sure you copy all 3 of them. Okay, yeah.
No idea.
It's so based on that.
Trees, yeah, trees and crops, I know trees are really popular for coming up with tree height, like forestry.
And
Um,
also like.
Yeah. Yep. Oh, yeah.
Also information about. student in the-
Sorry.
All that three other unknowns.
Yeah. So a lot of times the sun angle will be documented in metadata. So usually if you download an image, you can look in the metadata and come up with the sun angle, or at least the solar date that you can use to calculate the sun angle. Solar date just being 0 through 365. But yeah, so we could totally do that. And then you just come up with the measurements from your image. So like for this image, like we're gonna have a principal point. So the principal point's always gonna be the center. So let's say if we wanted to look at, say, this tower. So we can take the distance from our principal point here to the tower. That's gonna be our R. And our D is gonna be the side of the tower. That's the distance we actually want there. And then our H, our big H is gonna be the height of our sensor, which is gonna be in metadata as well. Or just call it elevation. If it's like a satellite, they'll have like a elevation of its orbit. Are unknown, which is the height of that building itself. Yeah, yep.
I was gonna-
Yeah, bigger times is awesome.
And they were doing, it was about 2 weeks ago.
Yes, yeah.
They- this person Day, he was on-
Mhm.
and then, the camera was off.
Yep.
They didn't know what time to go.
Yep.
Car, and then that car was like, people in that really was like, going to the- and they were able to- and he was-
Yeah. No, some of the things that you can measure from imagery and from geospatial.
Like,
Yeah, good. I enjoy this content.
Yes,
Are we just supposed to turn in the orthorhomatification file, or do you want to?
so go to the tasks document. I need to see all your images. So there, I tell you what. Yep. And like I was telling you, that there's more than just like the image file usually. So just make sure if you're moving one of these files, you're moving like the HDR file with the common name as well. That help you?
Yeah, good.
If you need to make sure you're sharing things correctly, let me know before you go and I can look at what you've moved around.
I want to make sure I'm sharing things correctly.
Okay.
One question before, so.
Have a good one, Dr. Phillips.
Yep. See you guys. Have fun at your event.
So now the dad is here.
Yep.
The GS is here, but the last one is here, it's also the dad, the line says different, it says RPCO.
Oh, that's okay. As long as I know which is which, it's fine.
And here, this is my output, hold on.
Yeah.
I don't see. It's just that here. That's one of the required, and it's here, but it's not even.
That's- So wait, which one are you missing? Are you missing that ortho?
DS dot dat.
The dark section. let's see. Is this your, so that's why you don't see it there. I don't know, got me. Yeah, so we can do this. Let's see if this here. So if this is weird, you ready for something weird? We're gonna go up here and click file and go to save as. That's, we're not saving the NB session, we're just saving the image that is highlighted here. So file, save as. Save it. That and. So here you go. Back to your correct location. What's up?
I'm still not convinced, but I've done the dark pixel thing 3 times and the photos look exactly the same. So I don't know if I'm doing it wrong.
Oh, yeah, I know.
Like, so is it, yeah, no, it's a real question.
I'm sure you're doing it correctly.
But like, they come out in maybe just as dark, if not darker. Like, you're supposed to do the region, so now I'm trying to capture a little bit more of the shadows, a little bit more of, like the buildings that have like shadows across, like you look nothing. And is this like, this is what this is? This is like the. This is like the product. This is what you're supposed to see. It looks dark still, it doesn't look like.
Well, I mean, it's not gonna be perfect. It's, so
I'm excited.
compare no, you have to click, you have to turn off the image over top right there. Yeah, there you go. So that's your light image. Now bring up your subtraction. The one you just turned off.
This region?
Yeah, sure. So now turn that on.
I
So-
think I'm doing something.
Wait until you get to Python.
Like I see the difference. But like, that like,
So you're compensating for the oversaturation of other areas of your image. And by doing that, you're making the dark areas.
Oh, they just, okay.
Okay,
So that's right.
I liked that.
So I guess it's the contrast that it's changed.
Yep, yeah, yeah, it's not exactly like making all of your dark areas not dark. It is just enhancing them for your eye.
Okay. Just make sure. Okay, that makes sense. I guess I'm just. Got it.
That's good. This is good for me.
Right, right.
No, I was expecting it to make everything, like, that's the original.
The rating metric calibration. Yeah, that's.
It doesn't have to be like my
Right.
previous
Yeah,
career,
yeah,
I was,
yeah.
I like coached college sports.
Okay.
And then
And
what,
like,
what exactly? is
Had like a really bad experience.
That's not.
And then I was
That's
like,
not a
fine, I
color
should go
thing,
back to
that's
my
like
roots.
a
I
lining.
really like.
Yes, yeah, that's an XYZ thing.
I was like thinking about how like I specialized in mineralogy and how that
Is it
wasn't a
like
good
when you?
idea. Wasn't a good idea. Like it was really fun,
That it,
but I don't want to do like
all
museum
of the
studies for
previous
this.
images to that same.
No, it does not. It's only setting your output. It doesn't even really set it, it just associates the spatial
I
location.
know, I was.
Oh,
Maybe
so
on the
you're not
graph
gonna notice it in the frame.
No, no, well, so if we were to get a truly like piece of raw imagery with no spatial location, no spectral information whatsoever, then we would have to move it to the location that it needs to be. We're probably gonna have to tilt it, rotate it. We'll fit it to the elevation surface because that's like how we have differing H's for our like calculations. And then we'll do the radiometric calibration or the radiance calibration and the dark areas or dark object subtraction.
Cool, sounds good.
Start.
Appreciate it.
Yeah,
Thank you.
no problem.
Cause also like we're 22.
I will be soon.
Yes, sir.
21.
Alright, so I think I got it all. And when it says it, turn it to zip, you literally just want to zip this left folder.
Highest level, yep.
Okay,
Yep.
cool. And like.
Yeah, you can just do like lab2_.
Okay.
That's perfect.
Sounds good.
And were you able to do stuff last week?
Yeah, I did. the same thing to everybody else.
She's making progress.
This image, we're not really making the dark areas lighter. It's the contrast of the rest of the. So. So.
General like that. If you have something to talk, that's good. Like whatever you did.
The main one that I see.
I'm not good at it. It's good with all my sources.
Some scoop traction.
Yeah, but if I have questions, that's all.
Yeah. But we got more of it. So maybe I should be doing quality presentation. I don't.
Well, you can see, I see a little bit there.
That's why I'm just thought, like, why would you just?
I mean, I see like maybe the one fellow. Yellow down there,
If I have a question, I'll ask.
Even like,
but yeah, that's,
like just doing this.
it's a really.
Sure, I got you.
Like the actual undergrad students.
Yeah, I want to go.
The atmospheric corrections are neater, because you can actually see the clouds being removed.
Yeah.
Right,
Yeah.
and
Once
so ultimately this is doing it in what we can see, but all the other bands as well, right? All the
Yeah,
stuff in the background,
absolutely.
the stuff that we can't see in the other bands.
Yep, yeah, so this is multi-spec data, so, you know, the non-optimal bands.
It's literally just, because as you said.
Okey doke.
I did the 3 for the.
Oh my gosh, didn't you read my directions?
You didn't say when you.
Told you put them in a zip folder.
Is this compressor output folder?
Okay, gotcha.
Is this?
So it needs all this.
That's what I. because
Show
that's
me
what
where
I
you're
said
working.
First, remember?
Right.
Try to just select one.
Your life, it will become easier to face anyways. Show me what you're gonna turn in. Everything in your NV out folder.
No, because I need this.
Oh, I don't need to see that digital elevation model again. So just, throw a underscore your last name on the end of that NV out folder and submit that one if it has the 3 files I'm looking for. Which it looks like it does.
So do we have to compress for a zip folder or a full folder?
I think you'll need a zip folder. Yep. I don't know. I've never tried to submit anything on Canvas in a unzipped folder. It's gonna say you have files open. You close down on NV. Nope, no, you did all your file saving when you were running those procedures. Back to file folder. I trust you know how to zip something. I don't need to stand here and watch you.
It needs all the metadata with the extra like, folder. Like it needs everything in the NV out folder.
Yeah, there's usually just supporting files,
Right.
like there's an NV header that allows you to view it in the NV. So yeah, just make sure you're getting all of the files with the common root name.
Is it done yet? So I'm over here doing the subtraction parameters. It says select this, right?
Yep.
But then it tells me it already exists. Am I overriding it? Am I doing something wrong?
It's just saying that it's already in the folder that you're trying to go to, and if you run it again, it's gonna correct it. Which is fine.
Is this where the dark fades away a little bit? Is this what I'm doing here?
The dark fades away, the dark never fades away. You should see a little bit of, it's, the dark areas might get a little bit lighter, but more what you see in the image is like these little areas of contrast will enhance a little bit. Yeah, it's kind of a, I don't know, you talk like you're gonna like correct all these images, and you're gonna be able to see everything. Because some of them I've seen more detail, like in this little line pop up. Others I've seen.
Is there a way to like learn and better? I've never, ever. This is very good.
Well, then you're in the right place.
It's very overwhelming to be like, there you go, dude, go.
Yeah. That's all
Yeah, no, this is. You're going.
Okay, I don't want to constantly like, I need them.
No, that's fine. That's
I'm on
fine.
12 now, I'm on 13. I'm on 14 now.
Nope, that's perfect.
You're like
It's all
so
normal.
Okay, so
So you're learning GIS and NV right now at the same time.
It's fun.
Yeah,
It's so fun.
yeah, that also.
Now, in a couple of weeks, you'll see that we do pretty much the same thing over and over again in NV. We're just sort of hang out with all these tools over in the box.
Yeah, I'm a big fan of repetition. I couldn't
Yeah.
remember last week, like, I tried to like download it on my laptop, it wouldn't work. I'm like,
Yeah. All right, so.
Yeah,
Yeah.
probably. That's
So you see the difference here?
Yeah, it's like. Look at the overall.
Yeah. So,
So it's not just correcting this one spot, it's.
no, well, in correcting this one spot, we're changing the statistics for the entire image. So by removing, so being displayed on a computer screen, all of these values are between 0 and 255. Okay? So we subtracted the darkest values from that. So we had 0 to 255, we chopped off the end. And now we're re-stretching everything to 0 to 255.
Okay.
So that's why we're seeing the brightening of our image, apparently. The apparent brightening.
Yeah.
And you can never say it's actually brightening, it's just what we see. So, and yes, me clicking this button, that's our dark area subtraction. So there you go.
Hey,
You happy with that? That's satisfying for you? What's up?
was the all the pixel size here. So I do have this, but like this meters here. I have a different window.
Oh.
I just need to put that.
Say statistics, if you click that, because we're working with it's three versions newer. Click statistics in your box there.
Oh,
Up, finish, yeah, there you go. Click export once for me, I just want to see what's there. Oh, that's not exciting at all. Go back to advanced and just accept.
I don't, it is, because I need to. It's actual meter stuff like this.
No, this is, all this is locked, so this is pulling this from somewhere. I'm not even sure,
Everything else
is that
okay.
the geoid correction? Or I don't even know what they mean by putting that below geoid correction. Is that doing a geoid correction, or is that telling us what the geoid correction is? Click finish
Am I in the right zone of the projection?
there. Yep, yeah, that's our image has metadata, so it's got the projection with it.
They just showed it in.
Yeah, it is. This stuff's nice and easy here at the beginning.
What?
It's all just that, it tells you right where to click. And I'm making this considerably nicer for everybody in here than I did last year at the beginning. Last year, this week, we were doing on paper radiance calculations. And I got terrible feedback for doing that.
Yeah, it's apparently still floating around because somebody was telling me about, oh, you're in 50/40.
Yeah,
Get ready to use your calculator.
yeah. Yeah, we're gonna hold off another week or two on actually doing the calculations by hand.
Open sample data.
Yeah.
Supposed to download.
No, so all these installations. I just gotta open.
Why work?
Changed my
I got two
preferences
kids,
To my St. Louis University.
I don't have, no, I
How many
can't.
classes?
So go to this.
Two.
Yeah.
Program files.
Yeah.
IntroRS.
I mean, I'm curious, like, study. Or the defense.
Yeah, exactly. So.
I'm not
and-
saying I'm silly, but I'm slow.
You're still getting more than I am.
It's cool. It's fun to show.
I still love pirates.
No.
That bad too.
See you later. Have a good one.
You as well.
It's just that really.
You tell me, come on.
The DM model,
Yeah.
but what are we looking at this? Is that like water going in?
They're valleys.
That look pretty.
Heck, yeah. Topography is awesome. It is. That's, I mean, that's what got me interested in studying topography, was just looking at it on a computer screen. It's so cool.
It looks like ice sticks or something.
Yeah, yeah, yeah. It looks like like ice is growing on a window on a cold day. There's actually, you can simulate real topography with math. It's pretty cool. You can like erode it over time and it'll look exactly like that. Everybody have any questions before I start packing up for the evening?
I just hope this works when I get home.
Well, if it doesn't, you got my email address. Can't guarantee I'll be working as late as you, but can usually give you a quick email answer. I don't know if it's any helpful to you, but hopefully it makes you feel a little bit better.
Is there a distinction between the different data files? The
Yeah.
.dats,
Sorry, what?
the .dats file?
And the like HDR file?
Yeah, I mean, I was just kind of poking around, but yeah, and so this one .dat file I opened has like a green version of the containers, but then this Oakland Port Ortho Photo 2 is nothing.
Like it's
So-
just like an empty.
Yeah, it's just an empty.
I didn't really investigate too much on what any of these images actually were. It's mostly just about how to open data.
Okay.
So, yeah, no, the one that we opened was a nice image. But yeah, the HDRs those are header files for NV.
Oh, okay, better, that makes sense.
And then the .dat is where the like actual data are
Actual
held.
data sets.
Yeah. And then there's sometimes one other one that what it is.
So is the, let's see.
So the only thing I see different between this and this is the bands. Because you've got band 1, 2, and 3 here for red, green, and blue, and this one, that's why it's
Yeah,
showing
okay.
you a blue. But yeah, that blue image could be one of the parameters for their deep learning model. Like maybe there's something with the shipping containers that the blue band shows them really good. It is an automated count of shipping containers in that image
Cool.
using deep learning.
Have you been to the Chicago Science Center? They have this really cool booth where you can dial in red, blue, and green. And then they have the color dots up there. And then, I mean, literally you can like have different intensities.
Mhm.
And so you can see like colors disappear because you only have, you know, the one color.
Yeah.
That was a really neat thing that, well, I thought was cool. My kids just loved playing with it.
Right, yeah.
So it's like getting the background of it was really cool. It's like a whole booth, you're like basically getting like you enter it.
Okay, nice.
So that you're just subject to that color.
Yeah. A color is cool, especially when you talk about like colors that aren't visible to
Yeah,
your naked eye.
no kidding. I mean, even in photography, you can get like infrared filters.
Yeah.
That you can screw in front of your lens and stuff, like that makes some really cool photos, like, you know, accentuate clouds and other things.
Yeah. No.
That I always wanted to play with, but one step at a time.
Yeah, right. Yeah. Maybe when you're retired. And even like the new Landsat satellites have a coastal aerosol band, which falls on the blue spectrum.
Oh,
So, I mean, they do a lot of coastal studies,
Yeah.
so they need to like be able to remove that like specific like blue haze.
yeah.
It is cool. What's up, Camilla?
So instead of doing this, instead of like choosing this close by, can we just like remove from? It's a different version.
It's different because that is only showing you what's displayed. But when you open a file, it loads it. Yeah.
It's same data.
There it is. So there you go. That's showing you everything that's loaded.
So I have to, okay, I'll click everything out except, this one. Close by,
Is that what it tells you to do?
except Tokyo. So that only remains, so except this one, everything else will be there. If I do so, the things will be out, but I'm supposed to have 3 images here, right? Because I'm gonna clean all the sample that you can.
Oh, no. Well, so I mean, that's not going to change anything in your folder.
But when I submit it, you don't want this sample stuff here because it was. previous.
Oh, correct. Yeah, because we created those samples just to show as an example.
Do you have anything?
Um, Where is, so here's your calibrated, this is your radiance calibration, right? So where is your dark area subtraction? This isn't your image though.
Oh, yeah. So I don't know if I
So,
can close that.
Yeah, don't close. Yep, we can find the location for these. So here's your dark area subtraction, right? Right click, go to metadata. So quick workaround, rather than go find that and copy it. Now that we have this highlighted, we can just go here and go to save as. And select this first one. And this is what we want, so that's fine.
Wait. Yes, no.
You're welcome. Have a good night. I don't, it's not. It should be this one. Can I copy that? I can't. Here, wait. This. You copy that for me? There you go.
And this is that. Is it done?
It should give it a .dat. Process.
I did something.
Yay!
Where did that go?
That's.
Are we
Oh,
crazy?
wait.
Where are
Let's
you?
go to, let's go.
Oh,
to-
NV out one. There you go. So this is where your other two are.
Oh, because anyone has all samples, I didn't want it, but that's fine.
Oh, so then here, I hope we do this.
That's okay. No,
So we
that's-
can grab everything. It's not a sample out of here. So to move these,
And then,
all we do is just make sure you have all the files with the common file name. Then we'll just paste it. Now I see everything that I want
You wanna
there.
see
Cal,
pictures?
DS, and the ortho. So that's good.
and dark pieces.
And you got your dark pixels in there. I don't even care to see those.
And just a zip this one. will
Yep,
do it.
zip that up and I would do like NB out underscore Dilmera. Is that how you say your last name?
Yeah,
Yeah,
perfect, thank you.
yeah, no problem.
No, I'm having, it's, my name is,
What, are you gonna say your name's weird?
no, I'm not. I'm just happy that you pronounced it right, because that's how it's supposed to be pronounced. But when China issued the passport, they put my name as my last name and my father's name as my first name.
Oh my
And
god.
the immigration just sent me email like, hey, your passport, your name is like this and everything else is like this. What's your name? And I was like, this is my name, but they want my birth certificate and everything. Like I have no access to get any data from my
Oh,
country. And like, how I'm supposed to prove that I'm Camilla, not my dad?
Yeah, yeah.
It's like, yeah, but yeah. That's my name, and that's my father's name. Oh, no.